So, what did we talk about last time? So last time, we sort of like, I don't know, talked about a handful of examples of convex MPC applications, just to give you a little taste of some of the things you can do with that that are sort of widely used for. We're gonna dig into a couple of those later in the class towards the end in some detail. Particularly, we're gonna talk about legged locomotion stuff and quadrupeds, and we're gonna do the rocket soft landing problem. So we're gonna do like a couple case studies on some of those. It'll be fun. So yeah, that stuff. And then we talked about nonlinear trajectory optimizations. We started that and sort of defined the problem. And then we talked about the differential dynamic programming / iterative LQR algorithm. And I basically like probably somewhat overwhelmed you with lots of math. Apologies, there was a lot. So in the interest of, like not having that kind of, just totally steamroll you with math, today we're going to sort of recap that at a high level and give you sort of the big picture and like some of the details, implementation details, and some of the extensions that you need to actually make it work in practice. And we'll talk a little bit about how you can go about handling constraints in DDP. Like, remember the way we talked about it last time, it's basically, looks like an LQR type of recursion. There's no provision for like actuator or state constraints in there. So we'll talk a little bit about how you can reason about constraints in these kind of DDP type algorithms, and maybe mention so-called free or minimum time problems as well, which don't fit super naturally into like the DDP setup. So these are problems like get to the goal as fast as possible, that kind of thing, which come up reasonably often. Okay, any questions about any of that stuff? Like anything from last time? Okay, hopefully today we'll get like a bit of we'll revisit the stuff from last time and give you hopefully like a little bit, of a recap, and it should make some more sense. I'm gonna try to turn off these stupid buzzing things on my phone also. Do not disturb me. Okay, cool. Here we go. So first thing is a little bit of a DDP recap. So remember, what we're trying to do here ultimately is solve, in this case, the unconstrained nonlinear trajectory optimization problem. That's what this is all about. And it looks like min over our x and u trajectories of some cost function that looks like, the stuff we've been looking at the whole time, where we've got a stage cost that gets added up over time, and then a terminal cost that's just on the last state. So that's our cost. And then we've got our nonlinear dynamics. Okay, so this is the problem we're solving. And the way the algorithm works, you have a backward path that looks like a slightly sort of generalized version of the Riccati stuff we know from LQR. And we start with our value function, and we Taylor expand it to second order in like a delta x. We got our v of x, we got our gradient term, and our Hessian term. And then we start that out at the end of the trajectory at time n by just looking at the terminal cost. So we got the Hessian of the terminal cost and the gradient of the terminal cost to kind of get us started. And then we go backwards with our like Bellman backup. And that looks like this. We minimize over our delta u the second order Taylor expansion of our action value function, which we're calling S in here, but you will mostly see that called Q in general. So that's what that looks like. And when you do that, you get the following stuff. You get delta U is equal to a feed forward term, i.e. like a constant delta vector, which we call D, and then a feedback term that looks just like and is exactly the LQR feedback controller. And then we plug that delta U back in to the value function, and we get our next cost to go Hessian and gradient. And we wrote all these matrices down last time. I'm just trying to summarize here. So if you want to get the definitions of these things, you can go look the stuff from last time and or in the code. And we're going to do some more code examples today. So you plug back in, you get big P and little p. Okay, so that's the whole thing. Okay, so that's the backward pass. We go backwards, we get these corrections on our controls, and we get this feedback policy. So now we have a new U trajectory. The next step of the algorithm is then to do a forward pass or forward rollout. And that I'm going to write it out in like kind of pseudocode form here with a line search. And it's just the Armijo rule that we've been doing all along applied to this kind of forward rollout. So the way we're going to do this, I'll write it kind of all the mess out. So we're going to compute the change in the total cost and as we go, and we'll do this. And we're going to start the rollout out. The new trajectory that we're getting after we apply this delta U, we're going to call that the prime trajectory. We're going to start out at time step 1 with x1 prime equal to x1. So like the initial state is given, right? We don't get to pick that. So we're starting at the initial conditions. And now we're just going to roll this out. It's going to look like this. So for k from 1 to n minus 1, we're going to calculate our new U. So we're going to call this U prime, and it's going to be our old U. And then we've got the feed forward and feedback terms, but we're going to put an alpha on there and do a line search on them. We're going to do the Armijo rule thing, the backtracking line search thing. And in particular, there's some little details here that are important. That alpha only goes on the D. It only goes on the feed forward term. It does not go on the feedback term. Okay, so that's what the U looks like. And then we're going to take that new U and plug it into the dynamics and get the next state. And then we're also going to calculate this sort of expected change in the cost, which looks like this. Terrible. Okay, so what this is the gradient, that GU guy is the gradient of the cost to go, evaluated at that time step. And then you're taking that and multiplying it by the update, by that D. So this is giving you, the reason we're doing this is so we can do Armijo. And remember, in Armijo, what we do is we try to calculate the expected decrease in the cost under the linearization, right? So in this case, that's the gradient of the cost with respect to U, which is that GU, times the step that we're taking, which is the D, and we're scaling it by alpha. Does that make sense? So in this case, it's the same thing we've been doing. The only difference here is we're doing this on a per time step basis. And so during the rollout, we're going to add this up, right? Make sense? So that's the expected change in cost under the linearization. And then we're going to take all that stuff and do our line search. which is exactly Armijo, just kind of applied in this context. So we start with alpha equals 1. And then we're going to do the following stuff. We're going to calculate our x prime, u prime, and delta j using that rollout procedure we just wrote down above. And that sort of, depends on x, u, e, k, and alpha. Then we're going to chop alpha down by some factor if we don't satisfy the Armijo conditions, which are the following, which again, this is the same stuff we've been doing. So we're going to evaluate the actual cost on our new trajectory, our x prime, u prime, and we want that to be we want this new guy to be less than our old cost minus this expected decrease with some tolerance on it, right? So that's the same stuff we had before. And then if that's, we're going to backtrack until that's satisfied. And then once it's satisfied, we're going to make our primes the new trajectory and repeat. And there's a few different, there's the question here of how you decide when you're done. And we're going to use the following. So the Ds, which are those feed-forward updates, we're going to basically do this until those updates are small, basically until it's not really taking steps anymore. So infinity norm means the largest, the largest single element of D until that's below some tolerance. And then like we had before, there's a handful of little hyperparameters in there. So in particular, the C, which is the factor we chop the step length down by, is usually sort of a half is pretty typical there. And then this B, which is the tolerance on like, how much we want it to like match the expected linear decrease. We usually make this pretty small, like 1e minus 4 to like 0.01, say, something like that. Okay. Does that make sense to everybody? Any questions about this? So we do backward stuff. Last time we basically derived the whole backward thing, which is all this crazy mess. And then we do forward rollout where we basically take those corrections, apply them, roll out the dynamics with those new controls, evaluate the cost, evaluate the expected cost decrease under the linearization, do our backtracking Armijo thing, chop the alpha down and repeat until we satisfy Armijo. And then we take that update and do it again. Cool. That's the general strategy. Okay. Everyone's cool with that. Now we'll go do stuff. Yeah.
I guess if I'm looking back through this, where we're doing like the forward rollout, we have this like for loop happening where we calculate these like u primes and x primes based on that singular value of alpha.
We pick an out. So we start at alpha 1, which is the full step, right? That's the full Newton step.
So do we go back through that if our line search is like, no, that step was too big?
Yeah, exactly. So here the step, think about it this way. The step you're taking is on the full trajectory. So to evaluate that thing, you got to roll out the dynamics along the full trajectory, even evaluate the cost, right? The cost depends on the entire trajectory and the updates on the entire trajectory, right?
Okay. So in our like pseudocode, when we're saying wall J of blah, blah, blah is less than this stuff, that's where we're
that's on the entire trajectory, to be clear. Yeah. So you do this rollout, you compute the entire new trajectory, which is like the primed trajectory. You've added the cost and you've already calculated the expected decrease in the cost. Kind of put all that together, check Armijo conditions, and then like if it's satisfied, you're good. You keep then the primes become the new x's and you do it again. Do a new backward pass, new forward pass. If not, you chop alpha in half, do another forward rollout, and evaluate the cost and the Armijo rule again until it's satisfied, right? So that part's the same, the Armijo stuff.
Thanks, love. Oh, he's playing with the cat.
Cool. All right, so let's do some code stuff. Check this out a little bit. There's some fun things in here.
Yeah.
All right, so everyone see that okay? Yeah, let's try. All right. Okay, so let's see. Now we have to apparently compile nonsense. Wait, it can take too long. So let's see. We're gonna do this. Do a few examples here. The first one's gonna be a cart pole. Does everyone know what a cart pole is? Anyone not seen a cart pole before? Pretty stock thing. So yeah, it's a little cart on wheels with a motor that can go back and forth on a track, and it's got a pendulum attached to the cart. And generally when you play with these things, the idea is you got this cart going back and forth, and you don't have direct control over the pendulum. You can only slide the cart back and forth. And the goal is to take the cart and slide it back and forth and get it to like swing the pendulum up. So it's one of these classic like under-actuated nonlinear systems that's used as like a control benchmark a lot. Okay, cool. So we're going to use a library to get those dynamics so we don't have to write them down ourselves. That's this robot zoo library. That's the continuous dynamics. So then we're going to do RK4 on them to discretize them in time. We're going to do this at like 20 hertz, which is reasonable. Then we're going to just write down a bunch of bookkeeping functions here to get all our Jacobians that we need. So these ones are just the A and B matrices. And then these ones are those tensor terms that we talked about last time. So this is like dA, dx, dB, dx, blah, blah, blah. You get the idea. Okay, so we're just going to do forward diff on all this stuff. And note what I'm doing is exactly what we wrote down last time, right? We're taking like df dx, which is A, and we're vectorizing it with vec, and then we're calling forward diff again on that thing. So we get this like really big Jacobian, right? Okay, so there's the second derivatives. This is just bookkeeping stuff. We're going to like try this over 5 seconds. Whatever, cost function. So here the cost, again, it's just quadratic stuff, but what we're doing here is essentially pretty small cost on the controls. These are like pretty modest, but we're putting a big terminal cost here. And the idea is that terminal cost is saying that we want to get it up by the end. So it's saying really what this is saying is like, I don't care too much about getting it up until the end of the trajectory. Like you better have it up at the swung up by the end of the trajectory. If I wanted to swing it up faster or sooner, I might jack up the stage costs, right? And you guys should go play with this, and it's kind of fun. Okay, stage cost, terminal cost, total cost function, cool. So we're gonna play around a little bit with this. This is the backward pass. It's exactly what we just wrote down. So there's a bunch of derivative stuff. And the thing that's gonna be fun here is we're gonna write down both the Gauss-Newton ILQR version, which is this one, and we're going to write down the full DDP, full Newton version, which is this one that has all these extra tensor terms, right? And we're going to try them both and see what happens. But this is basically exactly what we wrote down. This we're going to talk a little bit about. So remember when we did all this like nonlinear stuff before, when we did optimization, we often had to regularize the Hessians to get a descent direction. It turns out you got to do that here as well. So it's all the same stuff. We haven't quite talked, we'll talk about this in a sec. So we're first going to do this Gauss-Newton stuff. And yeah, it's exactly what we wrote down, so it shouldn't be any surprises. We need an initial guess, and here what we're going to do is we're going to start it at the origin hanging down, and then we have this goal state, which is, again, at the origin, but with the pendulum up. And we're going to initialize it with just like sitting at the initial state, and then with just a little bit of random noise on the controls. There's a really good reason to initialize it with some random noise on the controls. Anyone know why? Yeah, exactly. So yeah, basically if it's hanging straight down, there's this kind of weird phenomena here where like you want the gradient information to tell you to like swing up, right? If you're sitting right here, turns out like there's this ambiguity of whether I swing left or swing right. And it doesn't matter. The problem's completely symmetric about going left or right at the initial conditions. And so there's this like annoying symmetry in the problem, actually. That means the gradients are actually 0 if you're exactly at the bottom. So it's often a good idea to like actually put a little bit of random noise on these things to avoid things like your gradients being 0 at like weird configurations and stuff like that. This, by the way, has anyone heard of the hairy ball theorem? That's what this is, an instance of. It's a funny, it turns out that the deal there is the wording of the hairy ball theorem is you can't comb, it's actually like, usually people talk about tennis balls that are hairy. You can't comb it flat without it having a cowlick. So like the deal is you can't have a vector field on a sphere or a circle that has only one fixed point. So like the way, if I tried to like draw a circle, I want the gradients to point to the upward, equilibrium. Turns out you can't do that everywhere. You have to have at least 2 flat spots on a circle. The easy picture is like if I draw this, I want to be up here. So if I try drawing gradients that point me up, all over the place, I can do this all the way around. That kind of works. But then down here, what do I do? Like I can't have it have gradients pointing up everywhere. So it turns out that's a general property of spheres in n dimensions. Like you can't have just one fixed point. So this is like an instance of that. It's funny. Harry-Ball theorem just sounds funny. So look it up. Kind of cool. Okay, so that's what we're doing there. A little noise. Initial rollout, cost, whatever. Then we're gonna, here's the meat of the algorithm. So this is like the whole thing that we just wrote down. So we're gonna start with a backward pass, do the forward rollout with the line search, which is this stuff. This is just exactly what we just wrote down. Then we're gonna evaluate the cost. And there's a little bit of extra kind of like bookkeeping slash, bailout kind of stuff in here to make sure we're not messing things up. In particular, we have like a couple of little things here because it's nonlinear and sometimes if it's nasty problem instances, you can get like nans and bad things happening. So we're checking for that kind of thing. And then this is just what we just did though, right? So we chop the step size down, check our Miho, blah, 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 do this until we're happy. And then once we're happy, we update everything and that becomes the new trajectory. And then we repeat the whole thing, right? Okay, so let's go ahead and do this and see what happens. It's going to take a minute. My code is not fast, right? This is all, I'm calling forward diff a bunch and whatever. Okay, so that's 691 iterations. There's the cost. And this is like what the trajectories look like. It's very reasonable. And let's go like animate this and have a look. That looks sort of weird, but yeah, that's it. Okay, let's try some stuff now. I don't know, it looks kind of unphysical the way this is animated. Like that looks kind of wrong, right? I don't know. It's obeying the physics as we have written them down, but it does look kind of funky in here. Yeah, that's fine. I mean, it looks like it's kind of like torquing the pendulum around without doing a lot of swinging, but I mean, it is right according to the dynamics we have. Okay, so that's that. Okay, so let's keep this number in your head. So it's about 690 iterations. Let's go try the full DDP with all the extra tensor crap on it and see what happens. So we're then going to have to calculate these extra derivatives. And then we're going to comment this stuff out and try the ones with all these extra terms. So there's a couple things to notice here. So you notice I have this extra like is positive definite kind of check with all this regularization stuff in it. I actually have it set to display if it has to regularize, if it goes in here. And notice it didn't happen before, right? Because we were doing Gauss-Newton. And if you remember from before, we do Gauss-Newton, you don't have those extra curvature terms. And here our cost function's nice. So we didn't have to regularize because everything was benign. But as soon as we do this and we pick up those extra constraint curvature terms, it's going to mess us up a little bit. And you'll notice, let's go roll it out again and do it. Yeah, so now it's having to go in there and regularize the Hessian a bunch of times. So let's see. Okay, so remember before we took like 691 iterations. So here it's 552. So it's slightly fewer iterations than before. But also in terms of wall clock time, it was definitely slower. And that's because computing all those extra second derivatives is kind of expensive. So often we don't bother with this. Note also the solution you get is exactly the same. I didn't do anything different. You can like watch it. It's the same solution. So you get the same answer. In terms of iteration count, it may or may not actually converge a little bit faster, but in terms of wall clock time, it's usually not much of a win because it's way more expensive to compute. Okay, other things you can play around with. You guys should go play around with the code. Like some things in particular you should check out. If you go and play with the cost function, note the solution we just got, it basically did one pump to get up. If you make R bigger, if you make the control cost bigger, and you stretch out the length of the trajectory a little bit, you can get solutions that take multiple pumps and swing up slower because it's more expensive to use control effort, right? Stuff like that. So playing around with that, check it out. It's kind of fun. Any questions about this? Yeah.
Do something that wasn't like the pendulum straight up like at an angle or something. Is that going in and changing like the terminal two terms?
So that would be, so first of all, that's not an equilibrium point. So you can't actually sit still with the pendulum over there, right? Because it's under actuated. You could do some weird thing where you were moving, accelerating constantly and like have it, but that doesn't quite work, right? You could get it to some angle instantaneously at zero velocity at the end. And if you want to do that, what you would do is go change this X goal. you can make that anything you want. In fact, I don't even want to try it real quick. Do that and see what happens. So this is now going to try to get it to like pi over 2 at the end of the trajectory.
Is that like once it gets there, it stops? There's not like realistic.
Yeah, I mean, it looks like it didn't, yeah, it also like didn't converge because we didn't like give it enough iterations and stuff. But yeah, basically you can get it to get to here at the end if you wanted to at 0 velocity. So yeah, you can play with all this stuff. There's like kind of fun. Anybody else? Yeah.
So we do a similar thing in homework with LQR. Is the advantage of this is you don't need a reference trajectory to
This is generating the reference trajectory. So in fact, this gives you the reference trajectory. It also gives you the LQR tracking controller for free because those Ks that come out of here are the LQR controller. So if you just run this, you not only get the reference trajectory at the end, you also get the LQR tracking controller, which is kind of cool and kind of useful. In fact, that's quite useful if you're doing this online, because you can run this thing at like 10 hertz, say. You can use the LQR controller and run like a tracking controller at like 1000 hertz if you want to in between these solves. It's actually kind of useful. There's cool things you can do with that. Yeah.
In particular reason why you had delta J initialized as 1.
Yeah, I think that's a stupid, like I was just checking, where did that go? Yeah, it's because I checked, I think because of the conditions here, I don't want it to be 0 at the beginning because it'll automatically return. It's something dumb like that. Anybody else? Okay, so we got one more to do. Remember the Acrobot, right? We talked about that before. That's a double pendulum where you have one motor at the elbow joint, but you're unactuated at the shoulder. And it's called the Acrobot because it's a sort of like toy model of an acrobat on a trapeze where you have no ankle or no wrist torque. You're hanging on the bar. You can move at your waist, like bend your waist to do stuff. So that's kind of the idea here. Again, we're going to use a model, a library with a model in it, 20 hertz, RK4, same stuff as before. 10 seconds, 20 hertz, cost, same cost actually. We're going to put a big terminal cost to try to get it to swing up. Yeah, ILQR, we're going to not do the tensor stuff here. And then this is same deal. It's going to start down here and we're going to try to get it up here, right? And I think one thing to point out again is same deal. Like if you hang it straight down, the gradients are 0 and it won't do anything. So you need to perturb it a little bit. Basically, you have to break the symmetry. So it's either going to the left or going to the right at the beginning. So it can then figure out what it's doing. So we're going to give it some random noise. And then we're going to go solve it. This is the same code we just did. So yeah, a couple hundred iterations. Here's what that looks like. And we'll go animate it. Okay, that's cool. So now I want to show you something. So this is, so we've got this like random initial conditions situation happening here, right? Where I'm like initializing the use of this random thing. We just talked about this. If you go run this like, I don't know, a dozen times, you'll mostly get this answer. But once in 10 or 20 tries, you'll get a slightly different answer. And I want to show you that. I saved one of those. So we'll try that one real quick. So it's just slightly different, initial conditions. And it's basically the same cost, but look at the trajectory. It's quite different. Here's that solution. So it's like a qualitatively different trajectory, right? What's going on there? I don't have any thoughts. Why did that happen?
I mean, because you have some randomization at the start, there might be different local optima for like what a trajectory would work to follow.
Yeah, so that's exactly right. This is a non-convex problem, right? So it has potentially lots of local optima, and we're essentially doing Newton's method. It's going to land in whichever local minimum is the closest to where we started, essentially. Just like when we did the Newton's method stuff at the beginning of the class, if you have stuff with multiple local minima, it's the one you land in is kind of depends on where you start, right? Here we're starting with a random guess. We're going to land in the closest local minimum to where we started. And in this case, there's a handful of different solutions that have almost the same cost and like look pretty similar, and it's total random chance which one you end up in. And here we found two different local optima, basically. In practice, most of the time, we don't really care. Like in robotics applications like this, like usually, as long as it's getting where we want, it's obeying the torque limits and doesn't look stupid, then we're pretty much fine with it, right? So yeah, there's kind of generally could be there's actually infinite number of possible swing up solutions here, right? Similar to the other one, we can go play around with the cost here. Like if I jack up R and try this again, I can get solutions with like multiple pumps and stuff like that. We can try that real quick. I put that. Yeah, any other questions about this? Where did that go? So yeah, you should play with this. You can try all kinds of stuff. Like in particular, playing with the cost function and getting it to do different numbers of swing like pumps to get up is kind of fun. Yeah. Okay. Any questions about this? Local optima, should be aware of that. I think that's all there is to say about this. Yeah. All right. Yeah.
Change the location instead of being high somewhere else. Would it force the arm to be straight, or could it end like at an angle? Like,
So yeah, the key thing here is we're trying to swing it up to something that is in equilibrium where it can balance. If you swing it to some other location, like you could totally like have it terminal conditions be like somewhere random with zero velocity. It'll get there instantaneously at the end of the trajectory, but then it'll just fall down, right? So there are definitely solutions, weirder solutions to this. Like instead of like this, you could have a solution that's like this, that's also balanced. So if you found one of those and you wanted to swing it up to there, sure. You just
what would you add like a constraint to kind of force like the elbow to be bent, basically?
So remember, there's no constraints in here. So all I'm doing is I'm doing all of this with the cost function. So this is just I like set that final state. So yeah, actually, if I try something like, I don't know, just out of for fun here, if I make this a little bigger, we can try this again and see if we get a different number of punts. So yeah, so literally it's just this terminal cost being big is the only thing that's doing this right now. See if we get something different. Let's run it again. Oh, uh-oh, we got badness. So yeah, it's also, this is not very high quality code. Like there's definitely, things where you can get into trouble in here. So we need to do this. But yeah, you can do that for sure. And it would just come down to like that XN, that X goal that you're putting in the cost function. You would want to, if you wanted to find one of these that was slightly bent but still balanced, how would you do that? Okay, so what's the definition of an equilibrium point? Yeah, x dot equals 0 in our dynamics. So our dynamics equals 0, right? It's a root of the dynamics. So what you could do, for instance, is make what I would do. So there's two angles, right? And you want the velocity to be 0. So I would set this one to be something arbitrary, like say 10 degrees. And then I would use Newton's method to solve for the shoulder angle such that x dot 0, right? That's how, and then you get that, you plug that in as your goal state right here, and you'll swing up to that. And then you can wrap that in a LQR balancing controller once you get to the top. And
one of them has to be 0.
no, they all have to be 0. X dot equals 0. It's just a root. Yeah, I mean, that's just a root of the dynamics, right? Or equilibrium point, right? Cool. Anybody else? All right. So yeah, go play with this, play with the cost functions, mess around, it's fun. All right. So just to sum that up a little bit. Okay, so we did Carpal and Acrobot. And like, so one takeaway is, DDP can converge in fewer iterations. But ILQR often wins in wall clock time because the iterations are cheaper. What else? And yeah, in general, these problems are non-convex. Which means in general, you can land in different local optima based on your initial guess. Okay, questions about that? Yeah,
When you say initial guess, that's like the initial guess for your actuation over the full trajectory.
that's right. Yeah. So here we're solving for trajectories. Everything's about a trajectory. And you make an initial guess on the actually full control input trajectory in this case, right? So the way this works, remember, is we have the initial state, the initial conditions. We don't really get to guess the state trajectory. We only get to guess the controls. Then we roll those controls out with the dynamics to get, kind of to kick things off. And that's a key property of these kind of algorithms. They are always dynamically feasible. They always obey the dynamics because we're always doing rollouts, right? Okay, and then just to kind of finish off some of the details, you saw that we had to do regularization in there, which, makes sense. We had to do that, in Newton's method before, and there's nothing different here. It's a non-convex situation. It's Newton's method. So just like kind of the standard Newton situation, we had basically in this case, it's the cost to go and or the action value function, Hessians, can become indefinite. In the backward pass. And that makes bad things happen, right? It makes us go uphill instead of downhill on the cost function, which we don't like. So we need to regularize. So you definitely need to do it in the DDP kind of full Newton scenario. And even on ILQR, where maybe sometimes you don't strictly need to, it's often a good idea for numerical reasons. Because of floating point, messiness. If you're close to having, like a zero eigenvalue, it's not good. So just padding a little bit with the regularizer is generally a good idea for numerical reasons. So this is where it gets a little weird though. So like with the normal kind of Newton stuff we did before, it was very straightforward, right? You just like pad the Hessian. Here, there's options. It's a little kind of more subtle. There's several options. And here's kind of some of them. So the kind of like obvious thing would be to add a multiple of the identity to the action value Hessian. So to del squared S, which is basically what we do in like regular Newton. You could also just regularize the P's or the G's in the backward pass, like as necessary, which is kind of what we did before, right? In the backward pass, we would check P at each time step. If it was indefinite, we'd regularize it like kind of on the fly. So the P or the action value guy as needed. And so, yeah, the first one, what I mean is you just regularize the whole thing all the time, right? The second thing is, as you're going backward, you check it at every time step. And if you need to, you just do it at that time step. The other thing you can do is if you go stare at the equations here, it turns out you only actually need to invert in this. It's not in here. It's in the stuff from last time. In this min over u, the only matrix you actually have to invert is this GUU. So that's the only one that really needs to be full rank and blah, blah, blah. So you could also just regularize that one. The reason you can do that is because this is the only matrix to invert. And specifically, your D looks like GUU inverse GU, and your K looks like GUU inverse GUX. This option is maybe like reasonable for ILQR, where you're just doing this for like numerical conditioning reasons, but in the full DDP, it's probably not the move. Because in the DDP scenario, like your cost to go could be indefinite, which is bad. So this is just sort of for numerical reasons. Okay, and then yeah, like for ILQR, if your cost function is convex, like you shouldn't need to do it, but you might still need to because of floating point round off kind of reasons, conditioning reasons. So you should probably always just have a little regularizer in there. It's the same for doing Newton, in general. Okay. Any questions about that? All right. So that's kind of the whole thing. Now you know how to do ILQR. Some notes about this and pros, cons, that kind of thing. Because we're gonna do sort of a whole other class of algorithms for solving this nonlinear trajectory optimization problem. And so why you might prefer one over the other. Good things can be very fast. Both in terms of iterations and wall clock time. It's often one of the most efficient methods because it really exploits the full dynamic programming structure of the problem. Let's see. And another cool one is because we're always doing these forward rollouts, it's always dynamically feasible. So why you might care about this is if you need to stop early before the algorithms fully converge, like if you're in a real-time online scenario, this is very nice because you can just go run this on the robot and it'll obey physics. So it might be suboptimal, but it's feasible. And then the other cool thing that we kind of mentioned is it comes with this time varying LQR tracking controller for free. So not only does it give you like the feed forward, reference state and control trajectory, it also gives you this feedback LQR controller. And we kind of mentioned that like you can play fun tricks where you use that feedback controller, that LQR feedback controller that kind of comes out of this for free, to run the controller at a much higher rate online in between nonlinear solves. So like if you can only run the nonlinear solve at say 10 hertz, but you need to run the controller in the robot at like 500 hertz to stabilize it and get good performance, you can run this at 10 hertz, and then in between, you can run the LQR controller at a much higher rate, right? Okay, so bad stuff about it. One is that it does not natively handle constraints, right? So as we've done it so far, there's no sort of input, kind of like torque limits. There's no obstacle constraints, state constraints. We're going to talk in a second about how to incorporate some of that stuff. But out of the box, it doesn't do that. It also does not support, this is kind of a double-edged sword with the whole dynamically feasible thing. You're always doing rollouts. And so when you kick this thing off, when you initialize it, you have to guess the controls and then roll the dynamics out to get the states. You can't guess a state trajectory that's infeasible. That's actually very, very useful in a lot of situations. In particular, that's useful in like for example, like maze-like situations. We have a lot of obstacles. These methods often struggle with like getting around obstacles. So a really common move would be to use something like a sample-based planner, like an RRT, to find some kind of pose trajectory that makes it through the obstacles, and then use that as an initial guess of your state trajectory for this guy. It won't obey the dynamics because the RRT doesn't know anything about the dynamics. There's just sampling over, poses or whatever, but you can throw it in maybe and use that somehow to initialize a trajectory optimizer to get a dynamically feasible path right through the obstacles. That's a very common move. And unfortunately, like these algorithms are not really well suited to that. So yeah, like kind of bad for like maze or so-called bug trap problems. Basically problems with lots of obstacles. And then the final one is, we haven't really talked about this, but I'm just going to tell you this, and we can talk more about it if you're interested. These sort of algorithms generally, so anything with like a Riccati recursion, can suffer from numerical ill conditioning on long trajectories. It turns out the Riccati recursion is numerically unstable. That means in terms of like error propagation, from like floating point error, it's not great. So actually for very long trajectories where you're doing lots and lots of time steps, the numerical error due to floating point gets worse and worse and worse. And it can get pretty bad if you have like a poorly scaled kind of nasty problem. So that's the kind of, vanishing exploding gradient type phenomena, right? Okay. Any questions about any of that? Yeah,
Student with non-linear setting, we won't have any completeness variable.
definitely not. No, the best you can hope for is that it will converge to a local optimum from like any given starting point. And you can prove results like that, but they're honestly kind of meaningless in practice because you end up in floating point arithmetic, you can get in trouble. So even if they have these nice, like, sort of local convergence guarantees, in practice, they don't really hold up. They only hold up in exact, or infinite precision arithmetic in practice. And life is hard in general. So yeah, this is like getting into sort of voodoo-y, hard, bad territory. This stuff works great. You can definitely make it work, but it's not as like bulletproof as the convex stuff. You have to like actually kind of try a little bit harder and do some tuning and, trial and error kind of stuff to make this stuff work. Okay. Any other questions about this stuff? Okay, so let's see. Some quick notes about constraints then. So this stuff we talked about so far, no constraints. There's obviously we care about that. So there's people have been, messing around with how to handle constraints in these kind of methods for a long time. And there's a handful of different techniques. So let's see. There's a few different things you can do, many options, depending on the type of constraint. So in particular, if you just have torque limits, like just, kind of bounds on you, there's some special kind of like tricks you can play. The simplest one is to use what's called like a squashing function or a saturating nonlinearity. So this is a bit of a hack and maybe not the best way to go, but it's a common hack in practice. So I'll show you that. So maybe the most common one of these would be like Hanch. Or like any kind of sigmoidy function. So the idea is you have some function that, so the U's you're optimizing in the solver get plugged into this squashing function at the input to the dynamics. And then the U's that actually go into the dynamics are the ones after the squashing function. And the squashing function, the gist is you want something that's going to saturate out, but be kind of linear in the middle, right? So it's capturing this kind of behavior. So you would write this thing down such that it's bounded between U min and U max, and then kind of behaves roughly linearly, in the middle. And you'd like this thing. So, kind of the idea is it's gonna spit out some U tilde, which is squashed between the control bounds, and that's the one you're actually going to run. So for instance, here, if we use a tanh, it's going to look kind of like this. Like U max times tanh of like U over U max. Just kind of scale everything and rely on that saturating behavior to keep you within the control bounds. So this works. It's a very reasonable hack. It is effective. It will definitely make it satisfy the control limits. But it's adding additional nonlinearity to the problem, which can make it harder to solve and can make it take more iterations to converge. So that's not necessarily great. It's also, in general, going to give you a slightly like suboptimal solution. So because this thing's kind of like rounding things off, it'll give you solutions that are like smooth and don't ever quite get to the limits, which is actually maybe desirable in practice. It kind of smooths things out, makes it not like be super bang bang railing things all the time, which is not necessarily bad. But the kind of making it need more iterations to converge is not awesome. So there's a better option, which is so remember, we're doing this backward pass and we're solving this like min over U at each step in the backward pass. And what we did before was just take a gradient with respect to U, set it equals 0, blah, blah, blah. But you don't have to do that. remember when we did dynamic programming and Pontryagin and all this stuff, we made a whole point about how when you solve that min over u problem at each time step going backwards, you can just enforce the control limits explicitly there, right? So you can do that here. So if we do that, we just solve a box constrained QP in the backward pass instead of doing like the closed form answer, which is extremely cheap to do. And so you'll do this. You got delta U is argmin. Yes, it's slightly bad notation of this action value guy. So this is that backward thing, subject to like your torque limit constraints. So stuff like this. Right. So this is really easy to solve. Yeah. That's supposed to be x plus, oh yeah, delta x. Thanks. So yeah, instead of just, setting the gradient equal to 0 and solving for delta u in closed form, you just solve this little guy. And remember, S is quadratic. So, and we make it convex. So this is like a tiny QP. So it's really easy to solve this. Okay, so that's control limits, pretty easy. Turns out state constraints are a lot harder to deal with. So you will see many terrible things out there in the wild if you kind of get into this. It's very common to see people use like penalties. You just add penalties to the cost function to try to do this stuff. We talked about that at the beginning of the class, right? And said like, penalties are bad. They cause ill conditioning. You probably shouldn't do that. They never really satisfy the constraints also. So don't do this. That can make things ill-conditioned. So another option that is a better option is, well, what do you guys think? What would you do? Based on other things we have done in the class so far, and like things we did in particular at the beginning of the class, when we talked about constrained optimization a whole bunch. How did we teach you guys to do QPs? That whole like augmented Lagrangian thing. So the cool thing about the augmented Lagrangian method is it takes your constraints and it basically transforms them into a quadratic and a linear term in the cost function, right? The quadratic term is that quadratic penalty, and the linear term is that Lagrange multiplier term. So it looks just like a quadratic plus linear cost thing, which is exactly what's in this DDP ILQR stuff, right? Like the cost to go is quadratic plus linear. So the AL stuff slots right into this, like super cleanly, and kind of just works. So you can basically wrap the entire DDP algorithm in sort of like an outer augmented Lagrangian method. And this is maybe the like standard legit way to do state constraints in like a DDP type method. And our lab, like one of the first things we did in our lab like 4 or 5 years ago was to develop a solver called Altro that does exactly this. It's augmented Lagrangian trajectory optimizer. And it's just this. It's just like DDP with an augmented Lagrangian thing kind of smushed together. So that works pretty well. And is maybe like the best way to handle constraints in this framework. Yeah.
I guess I'm not really sure how these two bullets like how to reconcile them, because with the augmented Lagrangian, weren't we using penalty terms?
You're using a penalty term. So we talked about this like at the beginning of class, right? So the deal is if you crank that penalty up, so with a quadratic penalty, in theory, if you want to exactly satisfy the constraints, you have to jack the penalty weight up to infinity. And obviously you can't do that. And if you get it super big, it starts to make everything ill-conditioned and things just barf. So that's why you don't want to do that. And so with the augmented Lagrangian thing, we introduced this extra multiplier term. And the gist of that is you use the penalty to help you estimate the Lagrange multiplier, and you update the multipliers at each kind of AL iteration. And because you have that extra linear term in there with that Lagrange multiplier estimate, it lets you converge on the true Lagrange multiplier, in which case the penalty goes away and it converges, it turns out, for some finite value of the penalty weight, and you don't have to drive the penalty up super big. So it alleviates the ill conditioning stuff. I don't know. We talked about this a while back, so I don't know. Go check that stuff out again if you want. But yeah, that's kind of the reason for the augmented Lagrangian, is to fix that ill conditioning issue. Anybody else? Yeah.
I mean, it seems like you're not totally convinced that this is a good method. What are the downsides to this? Like the augmented Lagrangian wrapping. You just don't sound.
No, it works. It's like the thing. If you're gonna do DDP and you need to handle state constraints, this is probably the best way to go. Yeah, like definitely better than putting hacky penalty stuff in. There have been some attempts at doing interior point stuff also in like DDP. It's not great. I would not recommend that. It turns out like, yeah, you can't do the primal dual. Yeah, this is stuff we haven't really talked about in the class. If you want to know about this, come talk. There's a couple papers that have tried this. It doesn't work very well. So like basically, if you're going to do state constraints in DDP, do it this way. This is kind of the move. And yeah, that. Yeah.
Which discuss two methods there. In case of changing it, if you just keep school like yeah, we said for swatching function, we'll be like always be sure that we'll have feasible trajectories in this case, because we said we cannot have invisible stuff.
That, I mean, by construction, that U tilde can't exceed the control bounds, right? If we do this is a hack, to be clear. The squashing function thing is a hack. It works, but it's a hack. And if you're going to be serious about this, like you should probably do this thing instead, which is the more legit way to do it.
In this case, we have the feedback term K, right? How will that be affected because we're changing the?
This is a very good question. There's a little bit of a kind of subtle gotcha there. You also have to clamp them on the forward pass. And so there's a couple ways to do that. So if you want to know the details of this, there's a paper by Emo Todorov and a couple others called Control Limited Differential Dynamic Programming. We can send it out on the PIAs after this, where that was the first paper to really do this method. It's from like 10 years ago. And what they do is they solve this problem, the backward pass that clamps the U's. And then they also basically zero out the like, was it the rows of the K matrix that correspond to the saturated elements, which is effectively like same as like clamping them in the forward pass. Does that make sense? So there's some details in there, but yeah, you can check out the paper if you want the details. Okay, anything else about that? Let's see, how are we doing on time? Okay, so there's like some stuff we could say about minimum time problems. I don't know if that makes sense to do right now. Does that make sense to do right now? I don't know. I'm feeling tired. How are you guys feeling? I'm seeing some sleepy eyes and stuff. I'm with you. No, I'm like not feeling super energetic. Also, we've got like, I don't know, 10-ish minutes left. Thinking maybe it's time to call for today. We'll do this next time.